Hello and welcome everyone on this Flanders Make webinar on saving time and money by manufacturability analysis of CAD designs. My name is Philip Eikens, and together with my colleague Bieke de Kramer, in half an hour we will discuss a novel tool that we have developed. But first, some practical points. So please do save your questions, or you can already type them in the chat. My slide's not advancing. Okay. Please save all your questions. You can already type them in the chat as you think of them. And there's also no need to make a recording, as we will share this recording afterwards with you. So let's get started. What are we talking about today? Manufacturability is often really a big hurdle before any new product can go into production. So it's why there's really a need to describe all the geometric restrictions and limitations that apply for each specific process or even process variant. And this can take the form of so-called process handbooks that are readily available. But it can also be company-specific information for a novel process, for instance, where there's some maybe classified information on the specific limitations, and that's of course of high value. So in each case, if these so-called manufacturing rules are violated, there's a high risk of lead time delay in general. It can take the form of a need to rework the tooling or to recalibrate the machine. A lot of waste could be the result, and also sometimes the need to have new go back to the drawing board for a new design iteration. So of course that's all to be avoided. So we see here there's two main stakeholders involved in this process. You have on one hand the product designer, who is mainly looking at the functionality of the product, and on the other hand a manufacturing expert is involved, knowledgeable in the process. And we see that in current industrial practice there's a lot of iterations that happen, and either one of these stakeholders would evaluate manufacturability in a CAD, in a PLM software, a CAD environment, and indeed there are some functionalities that help to assist to check manufacturability, but this is often limited. It's often still very manual, so also error prone, and it's a lot of communication between these stakeholders is usually involved. So the challenge is really to streamline this process better, and ideally to just have one iteration where there's a single check of manufacturability, which is complete, which has a high degree of automation, and which is easily understood by both stakeholders. So the key here is, and the starting point is to capitalize on the manufacturing knowledge. And so what we will present next is, let's say, a tandem of two software tools that work together, where on the one hand we have a tool dedicated for the process expert. We call this the Knowledge Formalization Editor. So this formalizes manufacturing rules into a format which is then automatically available to the second tool, a rule evaluation software called CAD, and this is really tailored to the design engineer to use. So the design engineer can, as the design is being built, can independently and quickly check if there's some violations occurring for some manufacturing rules. Okay, so I will now first go a bit deeper in the Knowledge Formalization Editor myself, and then Bieke will give you some more insight into the manufacturing evaluation tool. The Knowledge Formalization Editor has been really conceived as a tool that is generic with respect to the manufacturing process, and which is also automatically usable for manufacturability assessment. This means also that, let's say, the domain-specific language should be considered, and that all the intrinsic, intuitive, geometric relations can be accounted for. And this involves, or this calls basically for new custom formalism. And so this is the formalization step. A new formalism into firstly a human readable format, a knowledge file. So I will go into detail on that next. But it's important here to see that this knowledge file is synced, let's say, with a machine interpretable counterpart with a parser which enables the machine executable code, and all the manufacturing data is also linked here with the help of a relational database. So the formalization step as a user is what you see, and here we use the integrated development environment of Xtext to really make this a very user-friendly tool. And I will show you this with this example here. So say that we want to impose a certain minimal diameter for all the bosses that we have in our designs. So I'll show you now the integrated development environment with a human readable file. So we just type a rule as a keyword for a new manufacturing rule, and then we give it a specific name. So you could see that, in fact, we had a template available to fill in all the required fields. And as name, for instance, we use boss diameter. Now we can add some metadata, like a description that gives a kind of a context to this rule, to that explains it also to the CAD engineer, and we can add a reference, a textbook reference, or another source. In this line for process, we select which process is applicable, and we have here a drop-down menu, and this is because in the same manufacturing file we have these processes defined. So we can select multiple, but now we just select injection molding. And as you can see on the top lines of this file, these different kinds of processes have been defined, so they're known to the environment, and they are interpreted on the fly. So we can have a material-specific rule if we want, but that's not the aim here. So we just use the keyword any to use any conceivable material. And then the key is really in the condition line. So where we need to fill in an expression that we can evaluate to true or false. And conceptually, we have to think about all the points at the material surface of the CAD design. And then we can use some intrinsic built-in functions. And in our case, we can use a function called radius, which gives locally the radius. So you also have some explanation available here for this built-in function. And we say that the radius with a factor of 2 needs to be larger than a certain limit, a certain bound, which we call boss diameter lower bound. And we have here an autocomplete for this value. And that is because this bound is also defined within the knowledge file, as you see here. So for a bound, we set both a critical bound and a warning bound level, and as default, and then we are able for material specific and or machine specific bound values to override this, as you see here in this example. And here we also have defined two machines that can have different properties to do the injection molding process. Another interesting feature is the error highlighting. So if I just remove one letter here, so this expression now does no longer have a meaning, because this is an unknown parameter, and we can see this with the small x in front, the red x in front of the line. We can click this error to see that, what the error is, and that there's indeed an easy fix available to use this already defined bound, and this removes the error. Lastly, we can add optional keyword here, valid in, where we specify that this rule doesn't need to be evaluated on the whole CAD surface, but within, in this case, a built-in CAD feature called the boss, which is also available from this drop-down menu. So besides these built-in features, there's also possibility to add user defined feature. And in fact, a boss is a special kind of rib with special curvature properties, and a rib is another built-in feature that we use. And this is what Vicky will talk about more in her examples. So just to summarize, for the Knowledge Formalization Editor, specifically for the process expert, so this is really a tool for a generic or any process to formalize and to manage, to keep up to date the manufacturing knowledge, to have a single source of truth, in fact. And while it's human readable, at the same time, it's also interpretable by other software. So it's built on these base functions for discrete points onto the CAD surface. So as I showed you, radius being one, but we also have the local thickness, local normal direction, and angle with respect to a particular other defined direction, like parting direction. And we have also properties of curvature and convexity. So with these very simple base tools, we can, or the process engineer can come up with very elaborate and complex features and rules, as you see again some examples here on the bottom of this slide. And with that, I would like to give the word to Pika.
Okay, good afternoon, everybody. I will now present the evaluation software CAD, which is the next step in the process. So this is for the design engineer to use. The screen is not advancing anymore for some.
Yeah, just. Yeah.
Okay, so here we want to evaluate automatically the manufacturability of CAD designs efficiently and robustly, of course, by using the knowledge that was formalized with the KFV presented by Philip. For this, we have developed 3 steps. A first one is to convert the CAD design to a discretized surface or volumetric elements on which we can actually evaluate all the rules. Secondly, we do a shape analysis of this discretization by building up basic properties such as the orientation, the curvature, and the dimensions to calculate every necessary property of the base functions that Philippe mentioned that you could use to define your rule. Thirdly, we automatically evaluate the rules and present them on your CAD design to give a manufacturability assessment to a designer. Hereby, we exploit the automatically detected features such as ribs and the defined rules in the formalized knowledge. To give a very concrete example, I will now go through how the software would compute the spacing of two solid ribs. If you would imagine the two light blue areas here as two ribs in a solid part, then often for many manufacturing processes, there is a rule that these should be spaced apart a significant distance so that they cannot be pasted together, for example, in some processes. This typically is set into a rule by saying that the distance has to be larger than a certain constant value times the nominal thickness of the part. First step is then to formalize this rule in the KFE, as Philippe showed also for the boss diameter, which means we will make a rule saying spacing of the solid ribs, where the mold thickness, which is the thickness of the space in between the ribs, where typically a mold, for example, would be, is bigger than a certain constant, which is one of the bound types that Philippe showed, and then times this nominal thickness, which I will go into more deeply later, here defined as a certain property of the thickness. This is then automatically parsed to a machine evaluable abstract syntax tree, as can be shown here. If we look more closely into this abstract syntax tree, we see that it's actually a breakdown of all the properties that we will need of our CAD design, and that our software must automatically calculate. We evaluate this tree from bottom to top to make sure that we have every leaf available. As first, we then need to first recognize the ribs where this feature is important. To detect ribs, we first calculate the distances between similar mold sites. So we detect a positive mold site, a negative mold site, and then we check for every point on the surface the distance perpendicular to the parting directions on this size. For some points, it means that there will be infinite distance and there is no actual width detected. For others, we really have a certain width calculated. Then to really detect the ribs, we implemented a rule-based feature detectant where we say that the points that are within a certain threshold for this width are a rib, because too thick features are often not recognized as ribs in such parts. This threshold can also be set by a parameter by your process engineer. This can then be automatically detected by our software, and as you see here, we here indeed detect the ribs as we define them in our design. As a next step, we of course need to calculate this nominal thickness, and for that we need to calculate the thickness. Here you can see our thickness evaluation on our part, which is based on a ball-based method. So we actually calculate the diameter of the largest inscribable ball at each location. Next, we want to calculate the nominal thickness. We did this as calculating actually the median of the thickness in everything that is not a rib. Our software can handle means, standard deviation, medians, minimal, and maximals of different areas in our part. First of all, we can calculate it over the whole part, so aggregate a certain value over your whole part, example, the maximal thickness of a full part. We can limit this to a feature, for example, the maximal thickness in a certain feature. This is what we use here. We use the median feature of everything that is not a rib to calculate our nominal thickness. Lastly, we can also limit it to instances. For example, if you want to calculate a certain value averaged over every instance separately. If we evaluate this then on our part, we see here that we indeed get the nominal thickness, a 1 value for our whole part. Next, we still need the mold thickness here, which calculates the largest distance to another side of the part. So actually the empty space around your part and how big that is. So the size of a mold, if you would imagine it being in there. Then we have every leaf of our tree here, because the rib spacing factor is a bound that was defined by your process engineer. And we can get let the machine, the software calculate the full rule, and you get the rule evaluation back on your design. We captured this all in a user-friendly GUI, which we will demonstrate now, finally. You first need to load your knowledge file from the process engineer, which gives them that. Then you load the CAD file in your software. Next, you select the rules that we want to evaluate. I now select here one rule, the draft angle, which means that we want to have a large enough draft angle for a mold to come loose from our part. You can select multiple rules at the same time, but I just select one for now. We need to set the parting direction on our part for this type of rule, which can be done automatically with a click, as I showed here. Then we can calculate the rule and evaluate it and show the evaluation, which you can see here on the 3D design. We see that there are also undercuts in this part, and they can be highlighted by our connected zones. They will highlight certain zones and make the other parts of the part more transparent so that you can really look for the parts that are undercut. This can, for example, these holes here in the front were not that obvious to see from the full part, but with the connected zones, you really your attention is drawn to them and you can find them back. We see that there is also a lot of red here. So we want to make a change, and our process engineer actually has a new material available that might be better suited here. So he can add an easy material that is better for this process, and then override the bound for this particular material. This can be on any machine, and we just say that the bounds for this material are way lower for the draft angle than the default bounds. If we then go back to our evaluation software, we can there reload the knowledge and re-evaluate the rule with the new material selected. And then we can see that a lot of our part now has become yellow. So it has changed from the critical to the warning bound. There are still some parts which are red, and our software also allows you to request the exact value at those points, which is, for example, here a value of exactly 0 degrees, which would never be demoldable in such a part.
Okay, thank you, Bieke. So that concludes what we wanted to show you today with the limited time we have. For sure, it's not an overview of all the functionality that we have in this software, but a glimpse or a first flavor to get acquainted with the workflow. Now, as an outlook, or you might wonder yourself now, yeah, would this mean something or have an added value for my process or my various processes that I'm working with? So of course that's a very good question to ask, and we'd like to yeah, let's say take the challenge. If you would challenge us with your own CAD design, we would really like to show you this in a workshop fashion, so on the spot. So for this, I think we can just take maybe 2 hours of time. It can be online or it can be on site. And then I think you can have a much better idea what this software can mean to your process workflow. So please feel free to apply or show your interest for this. So this concludes our session, except of course the Q&A. So please, if you have some questions, we are now ready to answer them.
Okay, thank you, Philippe and Bieke, for the nice presentation. We have a few questions already, so I'll just dive into them. Are there any plans to introduce a stronger type safety? For example, factor 3 can be specialized in types direction, offset, volume, yield rotation. This allows for validation, like for example, a direction mold. A direction should always be unit length, or a volume cannot have coordinates below 0, etc.
So for now, there is indeed not a lot of type safety in the KFE. Indeed, we aim it to be really for an expert process engineer who knows a bit what he is doing in that software. We could indeed, like the unit length for directions, make sure that always happens, though there are some safeties built in for that in the CAD software. There we do check that every vector that we work is normalized so that we won't have any problems calculating any angles or something that we do with the normals. Yeah, it could be something to look in further, but for now there are not a lot of type safeties there, no.
Okay, another question. Also, it seems that the concept of units is not present. A units of measurement system where properties do not only have a value, but also define the units in which they are expressed, would allow to prevent interpretation errors.
Yeah, so I didn't mention, or Philip didn't mention it explicitly, but there are so we have defined units of measurements to be millimeter, radians, and kilograms, I think. Yeah.
But you can also put them explicitly within the knowledge file, so that's key. So you can put a distance also 20 inches, for instance, and this will be interpreted correctly and converted to millimeters correctly under the hood.
So all most used units that we already have encountered are also explicit keywords in our KFE that are automatically recognized by the evaluation software afterwards. So millimeter can be used, the degree symbol can be used, as I showed in the example in the demonstration. I used the degree symbol, while actually our standard type of unit is radians for angles, so they can definitely be used.
Okay. Another question that we have, is there a standard knowledge file available to work with milling, welding, casting, or do we have to create it ourselves?
Yeah, well, we do have some kind of templates of some that give some examples and basically also show different functionalities of the software via examples. And these are with some common rules for injection molding and for some other processes. Yes. So
textbook rules. So the textbook rules, those we have a bit available. If you have really company-owned knowledge that is for specific process that you have in-house, where you have a process expert who knows by heart, this should always happen that way. Those are the things that really are worth capturing in such a software tool. But we can help you get started, of course, with these templates of the textbook knowledge rules.
Yes, and indeed, so if you're interested in a workshop, then we would together really build some of the knowledge, or we would show you how to write this knowledge on the spot and evaluate it on the spot with some CAD file example that you have.
Okay, maybe one last question. Can you maybe elaborate a little bit on the calculation time that is involved in the processing of the tools?
Yeah, so since we are not simulation-based, but purely geometric calculation-based, we really aim for an efficient system. And so the demonstration that I showed from CAD was a real-time recording. So it goes that fast to calculate an example. Some more complex rules can take a bit longer, but we aim to have everything really calculate on the spot so that the design engineer doesn't have to wait hours or days for an evaluation of his designs.
For very complex or for large CAD files and for some more complex calculation, you would have maybe a few minutes of waiting time, but not hours, for sure not. Also, the knowledge formalization editor that I showed was really on the fly as it appears, with the template suggestions and etc. It's really how you would use the software.
Okay, thank you very much. So we are at the end of the Q&A. There are no more questions, and I just hand over the word to Philippe one last time to wrap up this session.
Yes. So again, thank you all for joining and for tuning in. And please, if you would like to know more, then we would very much like to take up the challenge. So please get in touch with us if this is the case, and have a nice day.